Hello once again. It is hard to believe that I'm approaching the last video in my first semester Gen Chem 1 um, library. So y'all know you'll be sad when they're all over, but maybe they're helping. I don't know. Take the time to look at them and ask questions. Oh yeah, topic redox, reduction, oxidation. We'll hit this again second semester in heavy detail, because it has a lot to do with batteries and the use of electricity to force chemical reactions. But for now, our text just wants to introduce it and get you thinking about it. First of all, oxidation states, oxidation numbers. If I'm not mistaken, earlier in one of the earlier chapter, we did talk about this a little bit. Oxidation states or oxidation numbers are the positive or negative charge an element might take on if it were actually entering into a bond, and that bond were ionic, even if it's not ionic, like molecules. Still, sharing electrons are said to have certain oxidation states. So, two rules of thumb that I always go by are hydrogen is almost always a positive 1, and oxygen is almost always a negative 2. I said almost, didn't I? There are metal hydrides that have hydrogen as a negative 1, and there are peroxides and other weird oxide ions that might not have oxygen as a negative 2. Here's a picture from our textbook. Oh yeah, and pure elements. Pure elements are always zeros. Those are simple. You got to know that. Pure elements all by themselves in no bond at all, in their normal condition, have a zero oxidation number. And fluorine, I guess, is even more electronegative than oxygen, so it will also always like to get a negative 1. I've seen some oxygen-fluorine compounds where oxygen is forced to be a positive charge by the mean old vicious fluorine, which steals its electrons. If fluorine is very electronegative, it wants to get the negative negative electron density, negative oxidation state. Another way to think about it is the positions on the table. We've seen this a lot before. These main group elements. This is the +1 family, this is the +2 family, because this is just the 1s1, 2s1, 3s1, 4s1, 5s1, 6s1 orbitals, and that one electron on the outside loves to get dumped off to somebody. And these like to lose 2 electrons, these like to lose 3 electrons. These would like to lose 4 electrons, or it might be just as easy to gain 4 electrons. Noble gases don't want to do anything. Fluorine would rather gain a negative, so that they could look like have electron configuration as a noble gas would. And the negative 2 family likes to gain 2 electrons, 2 negative electrons. By the time you're to the nitrogen, phosphorus, and carbon silicon family, these guys can do just about whatever they're asked to do by the more or less electronegative elements they might be in combo with. So, examples of the abundant type. Lots of examples. I almost cursed. Sorry about that. Let's see. So, pure elements, pure elements, pure elements, pure elements. Pure elements, gold, mercury, bromine, molecule, still 0, fluorine. But then we get into the compounds. Oxygen is a negative 2, hydrogen is a +1, but there are 2 hydrogens, so 2 +1s and 2 minuses. So the neutral molecules all should add up to 0. 2 negative 2 for oxygen, 2 times negative 2 is negative 4. Carbon must be +4. But look here, carbon's a -4 because it's in the hydrogen. In with the hydrogen likes to be a +1. 4 times +1 is +4, -4. -3, +3. Salts are simple. It's just, well, usually they're simple. If it's a transition metal, you probably can figure out the charge on the transition metal from whatever negative ion it's with. I didn't include any examples here of that. +1, -1, +1, -2, but I have 2 pluses. +2, -1, but I have 2 minuses. +1, -1. Excuse me. Sulfur hexafluoride. Fluorine is very negative, electronegative, so it gets its -1 charge. 6 times -1 is -6, it's +6. -2 times 2 is -4, +4. Excuse me. Here, the nitrogen oxide compound, just -2, +2. So nitrogen is sort of forced to do whatever you ask it to do. Here's a weird one. P4O10. Oxygen, -2. 10 times -2 is -20. So this has to be positive 20. Oh yeah, and the ions don't add up to 0. The ions add up to whatever charge is on the ion. So 3 times negative 2 is negative 6, plus 5, negative 1. 3 times negative 2 is negative 6, plus 4, negative 2. 4 times negative 2 is negative 8, plus 5, negative 3. 4 times negative 2 is negative 8, plus 6, negative 2. So the polyatomic ions have to add up to whatever the charge on the ion is. Here's a mnemonic, kind of silly, but it does help you remember things. Oil rig. Oxidation is a loss of electrons, and reduction is the gain of electrons. Remember that. And if I lose negatives, I become more positive. So becoming more positive means your oxidation number goes up. And gaining negative electrons means your oxidation number goes down because you gain negatives. If you gain negatives, your oxidation number goes down. That's all I can say. Here's an example. Let me bump that up a little bit. So iron, metals. Metals love to lose electrons, and non-metals love to gain electrons. So here's iron rusting with oxygen. Oxygen itself gets reduced, but it oxidizes somebody else. So the oxygen oxidizes the iron to go from a 0 to a 3 plus. Is going from a 0 to a 3 plus a reduction? No, it's not a reduction, it's an oxidation. Is going from a 0 to a negative 2 a reduction? Yup. So the nonmetals like oxygen like to get reduced, and the metals like to get oxidized. And you can remember that too. If you can, you should. Try it. Metals like to lose electrons, non-metals like to gain electrons. It's just about that simple. Here's another example. Let me introduce the idea of an agent now. I said metals like to lose electrons, get oxidized. Non-metals like to gain electrons, get reduced. So chlorine's a good oxidizer. It's a good oxidizing agent. So we say the chlorine went from a 0 to a negative 1. That's reduced. But if you get reduced, you're called an oxidizing agent because you help someone else get reduced. You help someone else get oxidized. You help someone else lose their electrons. So the sodium lost electrons to become 1 electron to become a plus 1, gets oxidized. But that makes sodium the reducing agent. As crazy as this sounds, seems backwards, but it's not. If you think about it enough, practice it enough. Combustion, burning things. Oxygen's a good oxidizing agent. That's no surprise. But it itself, oxygen likes to get reduced. Here oxygen went from a 0 to a negative 2 in a couple different spots. So that's a drastic reduction. And the carbon went from a minus 4 up to a plus 4, seemingly losing 8 electrons. In a way, it did. So CH4 is a reducing agent. Here's something else to remember if you can. Fuels and foods are good reducing agents. They love to give up their electrons to become burned or become oxidized. Yeah, we'll say it that way. Something to think about. Here's a fun one. If you're brave, and maybe you are, pause the video right now and tell me who gets reduced and who gets oxidized. I've spelled it out for you. There's the permanganate, there's the iron 2 plus, there's an acid, there's the manganese 2 plus, there's the iron 3 plus, and then there's water. Which element gets reduced? Which element gets oxidized? And then, which compound is the oxidizing agent, and which compound is the reducing agent? Take a minute, feel brave, try it. Alright, you're back. I hope. You paused it. Who knows? You know. Your conscience knows. Permanganate's a strong oxidizing agent, and the manganese indeed goes from a 7 to a 2. From a 7 to a 2, that's a drastic reduction. It gets reduced. It gained 5 electrons, 5 negatives. The iron goes from a 2 plus to a 3 plus. That's going up in number. That's an oxidation. Yeah, so voila. I don't know what else I can say about that. Yeah, you could review it. Think about the transfer of electrons and what that means in terms of the agents. Here's another one. Pause the video if you can. Here we have a metal and an ion of a metal trading electrons. Who gets reduced? Who gets oxidized? Who's the oxidizing agent? Who's the reducing agent? Well, the pure elements, you remember, are zeros. Pure element and pure element, but the ions, +1 and +2. So copper goes from a 0 to a +2. That's not going down, that's going up. Copper gets oxidized. And silver goes from a +1 to a 0. That's getting reduced. Therefore, I call that an oxidizing agent. I know this because when I touch silver nitrate water, silver ions in the water, it kind of turns my skin brown. It oxidizes my skin. It doesn't hurt any. It takes a few days to flake away and go off, but and return back to normal. Here's one of our favorites, thermite. Thermite. Iron oxide plus aluminum goes to aluminum oxide plus iron. Pause the video. Who gets reduced? Who gets oxidized? Who's the oxidizing agent? Who's the reducing agent? Wish I had some Jeopardy music right now. All right, time's up. You paused the video, didn't you? Yeah. Iron, the 3+ here, and it goes to a 0. That's called a reduction. It gained negative electrons from the aluminum. Aluminum went from a 0 to a 3+. That's going up in number. So if iron got reduced, the iron oxide is actually an oxidizing agent. And if aluminum got oxidized, the aluminum is actually a reducing agent. Yay, one more. This is an active metal in water like sodium, potassium, calcium, etc. Pause the video. If you're brave. Who gets reduced? Who gets oxidized? What are the agents? All right, there you go. So calcium went from a 0 to a 2+. This is the +1 -2 combo, but that's called the hydroxide. It's a single negatively charged polyatomic ion. There are two of them. So 2 negatives and 2 positives. The water gets busted apart. +1 here for the hydrogen, but at least a couple of them go to 0. So that's a reduction. And the agents, well, if you get reduced, water is the oxidizing agent. And if you get oxidized, calcium is the reducing agent. That's a crazy idea. Got to practice that. Do what you can and remember some of those trends. All right, guys, thanks for watching. I'll see you in class.